Okay, so welcome everyone to lecture 19 of our CS2 classes. And I guess today we are going to study the topic which is the dearest to me amongst all the topics in the subject. But again, first of all, I would want to hear from you guys, how many of you are practicing or are about to start practicing or haven't yet started practicing at all about the topics that we have yet covered from the book itself. I'm not asking whether or not you have touched the past papers yet or something. Just the exercises and the questions that you had at the end of the chapter in the PDF that I have uploaded on the drive. So yes, should I call upon everyone to speak up?
Hi, good evening, Kashmira ma'am.
Just call me Kashmira or Jita. It's fine.
Yes, so I haven't really started. I'm thinking I'll start very soon. So when you said we can start from this lecture onwards, those who've missed the previous lectures, I thought that I'll finally start now.
Okay, all right. Thank you very much. What about others? Anvia, what about you? At least did you guys... Yeah, go on.
Ma'am, I had missed a few lectures at the beginning, so I was just going through it in this week. I mean, I just
Okay,
went
and
through
you
it.
understood, and you understood everything?
Yeah, pretty much.
Okay, good. Isha, what about you?
Hello.
Yes.
Yeah, ma'am. So I went through the notes from the PDF, but I haven't really started solving the sums in the PDF yet.
Okay. Savri, what about you?
Ma'am, I'm yet to do the risk models. The first two chapters are done. Just the risk models are in.
Okay. Mihir?
Yes, ma'am. I have finished loss distribution and reinsurance chapter. I am going to start risk model.
Okay. Vanshita, what about you?
Yes, ma'am. Same. I had practiced loss distributions and reinsurance, but last week I had my college internals, so I couldn't really go through risk models. I will start soon.
Yeah. It's no problem. And just to remind you guys, no one has yet sent me those negative binomial distributions, okay, from the risk model chapter. So as in when you're revising and you stumble upon the homework that I gave you guys, and maybe I shouldn't really give you guys a lot of time to submit, because if I do that, I see that, no one has really submitted that as yet. So again, if you want to submit. If you don't, it's not compulsory, but again, it's just for you guys' practice that I'm telling you guys that you should try your hands with differentiating, because this subject is all about differentiating well, and not only this part, but also the next part of the subject is going to contain a whole lot of differentiation and integration stuff. And there, and there it could be, even much more messier than it is here. So, okay, Ritik, welcome to the lectures. I guess this is your first lecture. So can we have a bit of introduction about you? What you do, and what you study maybe, and where you're based from, and why do you study actuarial science?
So hi, this is my first lecture in CS2. I'm studying my BA in Eco and Stats at KC College right now in my second year. And I just cleared my CS1 paper. And I've always been inclined towards stats and math in general. And so I guess that's why I was drawn towards this actuarial science part.
That is great to hear. So what do you do apart from studying, like any hobbies or anything?
Sorry?
What do you do apart from studies? Like what do you do for pastime?
Right. So I also play basketball and chess. I've been a national level chess player. So I guess that's why my inclination towards math and numbers has come from. So I like playing sports, and I also play the guitar for fun.
Oh, that's pretty good.
I'm inclined towards music.
I guess. Yeah, I guess we'll keep a session or something of you playing then.
Yeah.
Okay. All right. So let us start with today's lecture. And I guess before we start, I want to send across something in the WhatsApp group. So I've forwarded a picture which contains year-wise loss ratios. Does anyone here know what a loss ratio is? Have you guys ever heard of loss ratio? So loss ratio is actually just the ratio in percentages. So here if you see that the loss ratio is 17.4 for the year 1971, it means it is 17.4%. Okay. So in the numerator you have total claims paid, and in the denominator you have total premium collected. So basically if I may write on the board, what we have here is loss ratio, right? It would just be, claims paid upon the premium collected. And this is again, remember, in percentages, at least in the table that I have forwarded to you guys. So if I were to ask you guys, just see this data set, and the task, the objective of us is to figure out what the loss ratio will be in the year 1994. So what are the things that you would consider? So again, let me tell you guys, this data is actually, this data pertains to the hurricane losses. Okay, no, sorry, it's earthquake data. So yeah, it's about earthquake. Basically, it's about natural calamity. So forget it's earthquake. You can just assume it's any natural calamity. But again, I guess here it's earthquake data. So yeah, for someone who asked me, the chapter you're studying is extreme value theory. Is that the name of the chapter? Yeah, it's extreme value theory. Yeah. Okay, so would someone like to say what does it mean if I have, let's say, a loss ratio of 17.4 in the year 1971? What do you think it means if I have defined loss ratio in the way I have on the blackboard? Anyone? So you can unmute yourselves and speak up. Take some time to think. There's no hurry.
Can you repeat the question once? Sorry, just connected.
Okay, yeah, it's all right. So I've shared a picture in the group, and what you have to do is the basic objective of our discussion is that we have to predict the value of loss ratio for the year 1994. So let's say this year is 1993 and we know what has happened up until, let's say if we are considering it from Jan to December, we know what has happened up until December 1993. And now we are trying to, basically try to put some reserves aside to, cope up with the losses that might incur in the year 1994, which is why we as an insurance company, we are trying to see what is the loss ratio and how much of a percentage, much more than the premium that we expect to collect in the coming year, we should keep aside for the claims that we might have to incur in the following year. Okay, so this is the question, and this is the basic objective, I would say. And the question I asked you guys first is, what do you think it means if I have a loss ratio of 17.4 for the year 1971 in words? And I've defined loss ratio on the blackboard. So it is just, total claim paid upon the premium collected. And if you see 17.4 over there, it is actually 17.4%.
So it would mean if rupees 100 were collected as total premiums in 1971 January, then out of that, the insurance company had claims worth rupees 17.4.
The insurance company had claims worth rupees?
Sorry, not claims. They had paid claims worth rupees 17.4. If 100 were the premium collected in that year.
Okay. Yeah. That is actually the exact description, I would say. So for those who might not be able to hear her well, what she said was, if in the year 1971 the premium collected were 100 rupees, then A loss ratio of 17.4 says that the total claim amount paid was 17.4 rupees. I mean, if you're saying 100 rupees was the premium collected. Does everyone agree with this? Do you all understand what I just said and Urjita just explained?
Yes, ma'am.
Yeah, thank you. Okay, so now I mean, there's really nothing much in the table that I have sent across, but what is the very first thing that comes to your mind if you were to analyze this data set? What would you see? I mean, what do you see in this data set which might struck out? And is there anything that seems a bit odd in this data set? Any particular, let's say, value which is very low or which is very high? So as an actuarial analyst, what would you be happier with? Like what should be your maximum loss ratio that you would be happy with? And what number loss ratio should never exceed?
May I answer?
Yeah, sure, go on.
So 1989 figure is quite abnormal. It crosses 100, which means that the company will officially be in loss. So when you say what number the company should not cross so as to not what number no loss ratio should ever exceed, that would be 100.
And why do you think it should be 100?
Because if we are paying more than we have received from them, then we are officially in loss, and that is not a scenario insurance company wants to be in.
Yeah, right. So does everyone else understand what she just said? Who would like to summarize it again for everyone? Any volunteer? Ritik, would you want to summarize it?
Ma'am, I wasn't following fully, but
Okay, so just explain us what up until what were you able to follow?
so what loss ratio should it not exceed, right? So it shouldn't. I think it shouldn't exceed 100, but I wasn't sure why.
Okay, okay. Did anyone else get the reason of why it shouldn't exceed 100?
It shouldn't exceed 100 because that is basically the amount that you're receiving. So it's like if you're receiving 100 rupees in premium, you're paying back 129.8 rupees. So that is like you're paying out of your pocket. That's why.
Do you get it now, Ritik?
Okay, I figured.
Okay, so because the loss ratio over there is in percentage terms, if we have, let's say, a loss ratio of 129.8, what we are saying in essence is that 100 rupees premium mujhe mila, but the total claim amounts that I have paid out is 129.8, which has exceeded the premium that I collected, right? And over here, we are ignoring all the expenses and dividends and all those other stuff, which might affect the profit calculation. And over here, we just say that our profit is premium collected minus the claims paid, which is negative in this particular case, right? So we want to avoid certain situations. And over other cases, I guess everyone would be happier because these are like really low numbers. You don't see 98 anywhere. You don't see 87 anywhere. I think the other maximum that you have is just 22.8, right? Which was in the year 1987, before 1989's huge amount of 129. So again, if you were, let's say in the year 1988, trying to predict the loss ratio in 1989, on the basis of historical values that you have, what are the chances that your model would predict 129.8? Negligible, right? Because the other maximum that you observe from all of these cases is just the value of 22.8, right? So even if you consider all the standard deviation and all the variation that your model would incorporate within the confidence interval that you would have of the predictions for the next year's loss ratio, 129 would still seem a very far-fetched prediction based on the historical values, based on all of these historical values. Does everyone agree with this? Yes or no?
Yes, ma'am.
Yeah. So actually what happened was, there was, yeah, anyone would want to say something? Someone wanted to say something? Yes, Anvaya, you want to say something?
No, ma'am.
Okay. So now if I give you guys this data, and if I just ask you to take a wild guess of the minimum value and the maximum value for the loss ratio that you would want to estimate for the year 1994, what would your suggestions be? So I want you all to discuss among yourselves and come at a conclusion and tell me one final minimum value and one final maximum value. You guys can unmute yourselves. Anyone? Would you want to guess? Just a wild guess. I mean, I'm pretty sure it's not going to be correct, but I just want you guys to guess on the basis of the historical patterns and the trends that you see in the data set, assuming 1994 hasn't yet occurred. So please do not go out to Google and search what happened in 1994, but we just want like a wild guess. So Anvaya, what do you think?
Maybe 5.0.
Maybe 540. So, okay. Again, what do we know about point estimates? It could either be 100% correct or it could either be 100% wrong, right? So I want you guys to say some interval, okay? What is the minimum and what is the maximum loss ratio that you think might happen in such a scenario? So yeah, Anvya, what do you think? If anyone else has their guesses, just volunteer. Yes, Anvya?
Something between 4 to 5.
Something between 4 to 5. Okay. What about others? Isha, Mihir, Ritik, what do you guys think? So I have one estimate, which is 4 for minimum and 5 for maximum. And I want to hear from everyone. Savri, Shivani, Ujita, Vanshita.
I think minimum will be between 10 to 15.
Okay, so I am keeping 10. And for maximum, did you say 15?
Yes, ma'am.
Okay. What about others?
I want to go for 0 to 15.
You meant 15 or 5050?
No, 1 5. You're right.
1 5. Okay. Okay. All right. And what about the rest of you guys?
0 to 5.
0 to 5. Okay, good. And others? Vanshita? Isha? Shivani, Ritik?
I also think so. The question was what can happen, right? Not what might occur. So the possibilities or what might happen.
Yeah. So we are looking at loss ratios from earthquake. I mean, not exactly earthquake, forget about earthquake. But yeah, loss ratio for insurance companies basically.
Okay, so I'll also go with 0 to 20.
Okay, good. And what about the rest of you guys? Vanshita, Isha, and Ritik? Okay, all right, no worries. So Vanshita, you got any guesses? Ritik, what about you? Are you there? Can you guys hear me?
Yes, ma'am.
Okay, thank you, Shivani. So Vanshita and Ritik, can you guys hear us? Do you guys have any projections? Any forecasts? We could really use your help. I guess maybe they can't hear us or something. Vanshita? Oh, she's cut off. Ritik, can you hear us?
Sorry, ma'am, my audio disconnected in the middle.
Oh, okay, all right. So were you able to figure out and guess some minimum and maximum loss ratio for the 1994 year?
Probably 0 to 25.
0 to 25. Okay. So let me just add what I would guess in an ideal situation. And so seeing that, we have gone up until 47 in the year 1990, I would probably say that let us take that it could go from 0 to 50. I mean, I just want to round it off. Okay. So these are all the projections we have. And let us keep the minimum of the minimums and we keep the maximum of the maximums. Okay. So now our interval is 0 to 50. So we aren't basically models, we are just human predictors. So we guessed that our loss ratio for the year 1994 could be between 0 and 50. And just assume that similar predictions would have been for the year 1989 if it would have come to that. So just to reveal to you guys, the actual loss ratio for the year 1994 was 2272.7. Is anyone surprised? This is shocking, right? Because up until now, we have only seen a loss ratio which exceeded a value of 100 and it was only 129.8%, right? But what happened in the year 1994 is that the loss ratio was this much. Why? Because there was an earthquake at 6.6 scale, which hit California on January 17, 1994. So the loss for the property and the casualty and the destruction basically caused insurance companies a loss ratio as bigger as they would have never imagined prior to that year, right? And I think the similar kind of situation has happened right now as well. With the coronavirus in place, no one would have had even guessed in their dreams in the last year that unemployment would be so high, right? So what we have now is an event which someone would have never expected to happen, but it still has occurred, right? So what do we do now? The basic goal of we as analysts is to analyze the financial performance of a company and see whether it can maintain its stability, see whether it can continue its operations with profit, not only during the times when everything is going good, but also during the times when nothing in the economy is going as good as you would have imagined it to be. So such events are known as extreme events. So sometimes if you were to use this data set to predict, what we are taught in basic statistics classes is about outliers, right? You see that there are some outliers. So maybe you would have been told to remove this value of 129.8 from your analysis. If you were to, just looking at the normal scale operations and how much of a reserve that a company should keep aside to meet its expected losses in the coming year. So, but again, these unexpected events do not come calling off. You do not know when they're going to happen. So you have to have some reserves and some amount of guess at these extreme events as well. But we clearly see that if we use the models that we have known yet, we would have still not guessed a value which is as high as we recorded in the actual year, right? So this whole chapter is about trying to see the probability of these extreme events occurring and not making the mistake of underestimating such events. Because again, we do not know when these are going to happen. So it's in our interest to think that, it's not going to happen next year as well. Because the money that you could have kept aside as the reserves could have been invested somewhere else to maybe scale your business, or to maybe, it could have been given out as the dividends to the shareholders or something else. You could have just, distributed it as profits or raised the employees' wages or something else. But you didn't do that. You have to keep this amount aside as a reserve. So there is a cost as well to analyzing such numbers. But again, that cost is worth the saving it would do if, let's say, nothing goes well in the next year. So this whole chapter is going to be about, trying to fit distributions and learn something about these extreme kind of events. So what have we learned up until now? We saw that our claims actually are positively skewed, right? So can someone remind me of what do we have on the x-axis and what do we have on the y-axis? Anyone quickly? What is on the x-axis?
The amount of claims is on x-axis and the number of claims is on y-axis.
Exactly, and we have number of claims. So the reason we have a positively skewed distribution for the claim data set is because we see in general that occurrence of a large amount of claim is very low compared to a smaller amount of claims which occur at higher frequency compared to the higher amount of claims, right? So let us say we are looking at the data from 2009 till 2020. Again, let us say this is 2000, sorry. So if you are looking about the data set from 2000 till 2020, what would you observe? So let's say this is the times when there was financial crisis, right? 2007 to 2010 around. So this tail says that occurrence of a very larger amount. So again, I'm writing these numbers here, but remember on the x-axis, we have amount of claims. So what I'm doing is maybe I should not just write this here. So let's say I'm plotting this graph separately for each of these years. So if I'm looking for the year 2007, 2008, that was the time when the whole economy, not only in US, but in the UK, in India, and in all the major economies of the world, they experienced a market crash, right? There was a financial crisis, a recession, alike of what we have never yet seen before to that period. So what happened was a very larger amount of loss was seen. And now if you go back to model those events, you would see that these number of claims of such large amount were not these less. They were probably more than you would have imagined them to be. So now if you try to fit the normal approximation that we are so very, used to, and we are so very proud of using every single time, what would happen is, ideally, you underestimate the amount of losses, you underestimate actually the number of claims that you would get for such a high amount of losses. So what's really happening is that with extreme events, we know one thing for certain now, that if I want to model extreme events, if I want to see what is the maximum possible loss that my company can incur in the extreme worst case scenario, and if I have this question in mind, then my normal distributions and my normal theories do not really help me much. So there is another set of theoretical practice, which is termed as extreme value theory. So this whole arena revolves around, trying to analyze such extreme events. And these events are, categorized sometimes as, so we categorize them as LFHS. It means low frequency and high severity. So if you see, earthquake may not happen every year, right? But it does happen, let's say, once in a decade. So we know that the frequency of an earthquake happening is very low. But if at all an earthquake occurs, the amount of loss it is going to cause to my company is going to be so huge that it could also cost my company its solvency. My company could go bankrupt as well, depending on, the scenario and what kind of a loss we have incurred. So these kind of events are really unexpected. And I mean, what people usually do is treat it as outliers. You drop it out from the analysis. And then if you try to forecast, we know that my forecast is going to be very off the target, off of what I expect to, hedge against. So this is exactly, the reason why this theory was developed. And again, this theory wasn't developed, in financial realm. It was again derived from physics world and statistics world. And now we use it in finance. So I'll tell you guys the story about it as well. So now the question is, if we have this question to ourselves of how should I go about analyzing the extreme events, we have to come up with another set of theory, right? We cannot use the theories, we cannot use the models, we cannot use the distributions that we have yet studied. So now what we are going to do is, we are going to study some different kind of a theory. So to call it extreme value theory is what it will be called as. So again, if I were to draw just a normal distribution, let me just draw a normal distribution. So this is how we really draw a normal distribution. Its limits are minus infinity till infinity, right? And what do we see that this is the tail. So this is the left tail and this is the right tail, okay? So there are again two different kind of possibilities that you can see here. One is something which has a fatter tail and a higher peak than the normal distribution. So again, these kind of graphs are actually known as leptokurtic graph. So remember, leptokurtic means fat tails. And the kind where I drew the normal one, it's just mesocortic. Basically normal, everything. And the other scenario that you can incur is something which has, like lighter tails than the normal, and as well as, okay, maybe I should just draw it again. And it is, not as picked as the normal distribution as well. So these kind of curves are known as platykurtic. So an analogy, a great analogy to remember the names would be like, so leptokurtic looks a bit like kangaroos. So it's very much heighted, and platykurtic is short heighted. And I mean, as the platypus mammal is, right? It's very short heighted. And again, so now I have a question for you guys. For those who haven't really studied this subject before, what do you think is much more relevant to us? Leptokurtic, mesokurtic, or platykurtic when it comes to analyzing extreme events? So have a look at tails and see which kind of a tail we want to, consider when we are looking at extreme events. And by extreme events, I mean extreme events of losses, not of profits. We don't care if we get a huge profit, over here we're looking at losses. So anyone would want to guess? In financial terms, we know that, risk is associated with what? Returns, right? The returns that you get for, let's say, a stock that you have invested in and something else. But again, here, what I'm looking at with respect to the actuarial's point of view, we're looking at the risk associated in terms of the claim amounts, which we term as losses, which an insurance company might incur. So which one do you think is much more suitable for our analysis? Do we need tails which are fatter, or do we need tails which are lighter than the normal curve?
Ma'am, in this case also on the x-axis we are measuring the amount of claims, right?
Yeah. Forget about the x-axis. I mean, yeah, it's again the amount of claims and the number of claims again on the y-axis. It's the same. So what do we need? Do we want to analyze the case where the higher amount of claim has a higher chance of happening, or the higher amount of claim has even a lower chance of happening? What is it that we're looking at? What did you say?
Mesocortic.
Mesocortex. Okay, so mesocortic is what we have in the normal case. It is what we have in the normal scenario. But my question is about the extreme events where you might incur, a very large amount. So let's say if there were an earthquake, it would not only destroy one particular house, it would destroy a whole particular town or village, or let's say a whole, area, right? So all of those houses over there would go to their insurance company and claim on their property, which was insured by assumption, right? So the amount of expected losses they would have if there was an earthquake would be much more, because the number of claims that they would get is not only from one particular household, it is from all those particular households which were in that one particular area, right? So the number of claims that you get when there is such an extreme event occurring is much more, right, than what it would have been in the normal case. So what we want to look at is a leptokurtic kind of distribution, because it has fatter tails. So the area that we're trying to cover in the tail region is now much more, right? So let's say if you have a look here, this. Okay, let us try to see the distribution that we had here, right? If you fit a normal, it would give you a tail like this. But if you maybe fit a leptokurtic distribution, what would it give you? It would give you, something like this. So it has fatter tails, right? it would give you a bit fatter tails. So it would not underestimate the chances of this bigger amount of losses happening, at least as much as it would have been in the case if we were, using the normal distribution. Does this make sense to everyone? If you have any doubts, just ask me again, because this is the very reason why we are studying this chapter. And this chapter, mind you guys, wasn't there when I was studying this subject. So it's a newly added chapter, and this is a very important chapter as well. So does anyone have any doubts with all that I have explained up until now? Any questions, any queries? Okay, so I'll take that as a no. So there's actually a very famous financial statistician. I guess he's an economist as well. So he's called Nassim Nicholas Taleb, and he has a book called The Black Swan. And why does it, I mean, the name itself, right? We have the black swan. So we know that swans are usually white. So black swan is something which you might see once in a year, like once a lifetime event sort of a thing, right? So that book is all about analyzing these extreme kind of events. And he really says that, this normal distribution and this bell curve tells us close to nothing. And that is because it ignores the large deviations, and it makes us confident, even though we aren't, that we have in a way tamed the uncertainty that there exists in this world. But we do know, and we have had such experiences where we do know that, there's nothing that is certain, and we cannot really know anything sure 100%. So there is still a possibility, as small as it might be, that such kind of an event might occur and your company might incur huge losses. So you should be prepared for that. And this whole chapter is about, maybe not how you can prepare physically, but at least how you can be prepared in terms of money, with what you can, use to tame that uncertainty. So again, let us see what happens. So if you open your book, you see they have, mentioned a few reasons of a few difficulties that there are when you model extreme events. So again, I guess we have discussed a bit of those, and my favorite one is the most intuitive one that I feel is the last one. So what happens is, let us take the case of an earthquake. We just saw that if there is an earthquake, regardless of, the houses, each of the house in that one particular area is going to suffer a loss. So all of those people who claimed an insurance, who has, property insurance in place, they will go and claim that insurance with the insurance company. So what happened was, during all the analysis that we have here done, what was the basic assumption that we used? We always said that, my events are independent and identically distributed. So in such extreme events, are these events really independent? This assumption does not hold true now, because we know that if there is an earthquake, the whole town is suffering. So it's not only that one particular house in one particular lane is suffering, all of the town has to suffer. So if we incur huge losses from one particular house, there is an increased chance of incurring losses from the other houses as well, right? In case of an extreme event, which is the earthquake here. So this extreme value theory was actually, very widely applicable in environmental sciences. So we'll see the methods that we have. I mean, you'll see the intuition behind it applicable really well in terms of, the environmental sciences, because again, earthquake and windstorms and hurricanes, and these are the extreme events, right? And you want to insure against them. So that's it. And in engineering as well. So let's say if you were supposed to build a dam, what you will have to see is what is the highest possible level that the sea can rise up to, right? And you will again have the cost and the associate trade-off again, because to build dam, it takes huge costs as well. But again, if you build a dam which is not that quite well suited, and if the sea level rises, then there's no point of having a dam in place. So you have that trade-off about, saving the cost and saving the lives if at all an extreme event happens. So this topic is really important. And again, this topic is not that widely used even yet in actuarial sciences than it is in the other sciences, especially hardcore sciences. So, okay, let us start with it. Finally, we have had a huge discussion about, what this topic is about and what is the reason behind this discussion and this invention and discovery of the extreme value theory that we have to study now. So let us say I have observed some data. Okay. So again, I'm plotting, let's say just, some data values here. Okay, just consider that there is no one in vertical line. I mean, there is one data set for each year, let's say, okay. I'm just plotting these for illustration purposes. And maybe I should erase this. This is in one line. Okay. Yeah. I guess, yeah. So what I have here are the different kind of losses that you can incur. Okay. So remember, this is not the usual graph that I have. So I have time on the x-axis, which might represent years or it might represent months. Let us say it is months and so on. And on the y-axis, I have the loss. So this is my loss pertaining to each and every month across this time period. Okay. So if I want to have a look at the extreme events, which losses from these do you think are extreme? So maybe this is extreme, right? This also seem extremes, and maybe if we have a look, we can maybe call these and these as extremes. Okay. So in a normal case scenario, I'm calling these guys as my extreme events. So now what I have to do is, if I have to figure out something for my time t plus 1 here, again, if I model each of these, if I have my data values for each of these data points, what would happen is, it will underestimate the chance of that higher loss happening, because I would also have these lower losses taken into consideration. But again, what we are questioning ourselves of is, what is the worst possible loss that my company can incur? So what you want to do is, you want to forget about these data points and you only take into consideration these extreme events, and you just consider these as your data points. So now instead of having all of these data points, you only have 1, 2, 3, 4, and 5. So these are the 5 data values that you have. And now if you only take these into consideration and try to predict what can happen next, this gives you, a reasonable amount of guess as to what loss your company can incur in a worst case scenario. Does this make sense to everyone? Do you guys understand what I'm trying to say?
Yes.
Thank you, Vijita. What about others?
Yes.
Yes, ma'am.
Okay. Thank you, everyone. So this is the idea. Now what we're going to do is, there are different methods that you can use to analyze these extreme data points. So let me maybe just first draw a distribution. So let's say if this is what I have, then I'm drawing a distribution which includes all of these points. Okay. If I'm including all of these points, let's say my distribution looks something like this. Okay. So this distribution I'm calling as my parent distribution, or in your book, they say it is underlying distribution. Okay. But again, remember, this is not what we care about, right? Forget about all of these events. I only care about these extreme events. So if I were to plot these events, the distribution would look a bit like this here, right? So I would have a separate distribution which pertains to only extreme events. So I'm defining my extreme events as the values of my loss exceeding this particular limit. So I have another distribution for these events here. And this distribution will be my child distribution. So we're going to refer this distribution to as child distribution. And this whole chapter is about this child distribution. And you guys will be surprised to see actually how easy it is to analyze extreme events than it is, to analyze this. I mean, at least from what you guys have to study in this subject, not in the actual, but at least with what all you have in this subject. Okay, so let us start with the very first method that we have. And again, what I'm going to do is, I'm going to divide all of these. Okay, even before I explain to you guys this method, let me ask you guys one question. If I were to only take one extreme out of these data points, I would only take probably this, right? Because this is my extreme most event out of all these data points. So if I were to make a prediction based on only one extreme data, so go back in time when I gave you guys a picture on the WhatsApp group about the California earthquake data set, we had only one extreme event, right? Which was a loss ratio of 120, 130 approximately, right? So that was the case where we only witnessed one extreme event. So if you would have taken that extreme event into consideration, you would only have one data point, right? And now if you want to try to model what another extreme event, if at all, you can incur within, the next year, what would you say? Using one data point, what all can you say? So again, remember, looking at this whole data and taking only one extreme into account is really not the best way, right? Because even though you might be, 100% optimistic about your results and everything, doing statistics based on only one observation, it's just downright lie. You should never do that. I mean, so that is where this method actually comes into picture. So what this first method tells you is, you should first of all divide your timeline into blocks. So I'm talking about blocks here, usual normal blocks that we have. Okay. Oops. Yeah. So this event is known as blocking method. So what we are going to do is, now I'm going to create some blocks here. So let us say I've divided my time, and again, these would have to be, equally spaced time intervals. So I've divided my time into 4 different blocks. So this is a first, second, third, fourth block that I have. Okay. And now I'm trying to model extreme events from each of these blocks. So again, if you see, I should, just maybe ignore this data set here, right? So let me just have one data point there, which we ignored. So I have one extreme value from this block, one extreme value from this block, one extreme value from this block, and another extreme value from this block. Let me just, yeah. So my data set here, if I'm analyzing extremes, would only be this, which is my x1, this is my x2, this is my x3, and this is my x4. So what I will have is x1, x2, x3, x4. And this is all that I have observed. These are my data points, okay? And then I'm going to fit the model of the, so I'm going to tell you guys which distribution we will use, and we'll fit that distribution to this data set to predict what extreme losses you can incur in the next period. So Up until now, is this clear to everyone? Do you guys understand the way I have blocked? So again, remember the number of blocks you have, the number of data points you're going to have, because from each block, you're taking the extremum value, right? So the number of blocks you have, the number of data points you're going to have in your data set. All right. So now if I'm going to employ this technique, one question I have as a statistician who would use this method is, how many blocks should I create, right? Would anyone want to guess? I mean, so let us say if I'm looking at a time period, and blocking actually made much more sense with the environment in picture, right? You have these seasons and the blocking would come naturally. And that doesn't happen in the case of finance or in the case of insurance sector. Maybe it does. So let's say if it's a monsoon time, there is a chance that there might be a flood. There's an increased chance that there might be a flood compared to as if it were sunny. So I guess that's there. But again, what you can do is maybe divide this into quarters, or again, it depends on the kind of analysis you're doing. So if you're looking at earthquake, you might want to have a look at, these droughts and everything else that you can have, and other various factors that might affect earthquake, which I'm probably not the best person to ask the answer of. So, okay. Now, if I were to decide how many blocks should I have? I have a conundrum in statistical sense. And that is, let us say if I decide to create more blocks within these blocks. Okay, so now I'm trying to create one more block, let's say here. Forget that this is a data set, okay? This is another block, and then I have this block, and then I have this block. Okay, so now previously we had 4 blocks, right? Now we would have 8 blocks. So now if I were to point out again at the extreme events, so from this block I have this as my extreme event. From this block I would have this. From this block I have this here, here, and here, right? So now what you see has happened is, as and when I increased the number of blocks, I have more data points, right? So instead of 4x's, what I have something from x1 till x8, right? Let's say this is my x5, x6, x7, and x8, right? I have 4 more observations. And what does my theory say? Up until now, we know that if I am to fit any distribution to the data that I have, the more number of observations I have, the more accurate my prediction is going to be. Do you guys agree with this? Yes or no? So I'm saying the more number of values I have of the observed data, the more accurate the fit of my distribution is going to be, which will render even a more accurate forecast value, right? But this is a big but. So what has happened here? Can someone see? If I increase the number of observations I have, what is the disadvantage that I have? Is there any disadvantage?
Ma'am, so the values that we didn't consider as extremes earlier, even those are considered as extremes now.
Precisely. This is a very good answer, Isha. Thank you very much. So again, now you see this may not qualify as an extreme value, right? I mean, this is just the normal loss that you might incur. So now if you're trying to fit a distribution of extremes, you want to try to avoid those normal losses value, right? Because that will in a way underestimate the chance and the actual amount of the extreme loss that you might incur. So now there is a bit of a dilution, I would say, in terms of the extreme values that you want to capture, right? But this is a trade-off that you have to deal with. And again, you will have simulations and you'll have a set of 1,000 models running when you're actually practicing this. So it wouldn't take you much time, to decide between keeping more blocks or keeping less number of blocks. And again, it depends on the kind of accuracy that you're looking at. So not always you want your model to be like, perfectly accurate in terms of all the parameters. Sometimes you are willing to compromise with a model's accuracy on certain parameters, not always, but that does happen sometime. And this is much more or less like, the bias variance trade-off. So if you guys know about that from finance theory or something, that's really something that you should have a look at. So, okay, this is just one method. So that's it. This is the first method that we have to analyze the extreme events out of the two methods that we are going to study in this chapter. This is known as maximum blocking method. So maybe I'll just pull up my book here and you guys can go through the example that we have in the book. Let's look at page number. Yeah, so can you guys see this data set? So let us look at what the question is trying to ask us. So they have defined for us the block size. What do you mean by block size? Block size means the number of values that you're going to have within each block. So they're saying determine the values of xm where the block size is n equals to 5. So what is my xm? My xm is just the maximum amount of out of all the x's. So my xm is just the maximum of this thing. And this n here is the size of each block. So let me just do it for you guys here, and it's really easy. So determine the values of xm where the block size is 5. So let us say if I have a block size of 5, so I'll basically be looking at these values. So 5, 10, 15, 20, and so on, right? So my xm for these values would be what? Would anyone want to guess? What is the maximum value out of these values? Claim amount? 1 or 2, right? Then for the next set, it's going to be 108. Sorry, 152 over here. Yeah. Thank you. Yeah, so it's going to be 152, and then you have 147, and then here you would have 128. So forget about the rest. I mean, you just have to carry on with the same thing. So if you have a look here, you get the same values, right? And you can do so for all the values you get for the block sizes that we are looking at. Okay. So next up, they say if at all we have a block size of n equal to 10, then what's going to happen? So let us see what happens. So let us say if I'm looking at block size of 10, I would be capping here and the next cap would be here, right? So you don't have to necessarily consider all of these values, just take the maximum out of this. So we have 152 here and here I would have, let's say 147, right? So if you see, you do get something similar here. 152, 147 and so on. So what happens is, if you have a block size of 5, you get 12 set of values. And if you have a block size of 10, you get only 6 values. But if you have a closer look, as Isha rightly pointed out, these clearly look extreme, right? And these incorporate like 102, 128, 113, 84, 94. Over here, we see no value which is lesser than 100. So this again right here explains, the trade-off that we had a look at. So the trade-off between the block size and the values of xm that we'll use to fit the extreme value distribution. And we'll have a look at what distribution that is right away. Any doubts with this question? Anyone? No doubts? This seems easy, right? So this whole chapter is actually just about this. And I guess you're going to fit the distributions in the similar manner, which we did up until now. So it's just that the distributions will differ and they would be just a bit complex in terms of looking, not in terms of using and doing the math and all. So, okay, there is a magic that will happen now. So what I would say is, let us just first write the data values that we have. So remember, I have x1, x2, up until xn. So these are all of my extreme data set. So I'm just going to write it as xm here. Okay, so this would be essentially maximum of those, right? So this is my xm, which will be maximum of these, where n is my block size. Okay, and what I will have my data set is basically m1, xm2 till let's say xm small m, where my small m is the number of blocks I have, right? So the number of blocks you make is the number of data points you're going to have to fit a distribution to. So does anyone remember the result of central limit theorem? What did it say? And what were the assumptions we made in that central limit theorem? Anyone? Do you guys remember central limit theorem? We even used it in a recent question, right? I guess in the risk models chapter. So remember, when I'm talking about central limit theorem, I'm talking about the averages, this sum, right? So what does it say is that if I'm looking at this sum of independent and identical values, it will follow normal distribution in limit asymptotically when I have n value high enough, right? Do you guys agree? So these kind of approximations that we have using CLT is always pertaining to normal, right? We say that if you're looking at the sum of the average, sum of the values, it will follow normal distribution if my n is bigger enough. The similar thing is happening here with the extreme value theory. What it says is, instead of sum, now we are looking at the maximum. So previously in CLT, we looked at the sum of values, and now we are going to look at the maximum of values. So what my extreme value theory says is that the maximum of all the values will follow a generalized extreme value distribution, which I'm just going to reveal now. If again my data is IID. So again, you are assuming that these XMs are IID. Okay. So you know that this XM1 is the total loss incurred where you experienced one particular earthquake, right? So if you were looking inside this XM1, you would see that all of these various losses from different portfolios or policies aren't independent, but this loss as a whole from one particular earthquake is independent of this loss from, let's say, another hurricane or another flood or something else. So this is my assumption here. And this is what I'm going to be working with now to analyze the distribution that I will try to fit to the data set that I have. So again, remember, what are we looking at? We're looking at the maximum, right? So what I'm going to do right now is, let me just maybe write this. So do you guys know what asymptotically means? So when I'm saying that, CLT is asymptotic limiting distribution. So CLT is asymptotic distribution is normal, right? So whenever I say asymptotic, it just means that I have a bigger enough n, and it wouldn't be a compromise to say that my n goes to infinity, because it essentially doesn't change the analysis significantly. So you just say that your n goes to infinity, and that's it. So now what I'm looking at is a limiting distribution, right? So it's downright now that I mention the limits and I see what distribution it follows. So are you guys ready to know the distribution that fits everything? So let us say I'm going to write limit n goes to infinity. And what I have to figure out is the probability that my xm, so this is my xm that I'm going to be looking at. So this is just, okay, so I guess they have defined this as their xm. I mean, forget about this. You define this as your xm data set. So this is what you're looking at. And what you have to see is check for its distribution. So what we generally do is we see if it is less than or equal to some particular value, small x, right? But again, if you guys remember, in this CLT as well, we used to do some standardization. And that is the same thing we're going to do now. So first of all, let me assume that my distribution for x is f of x, right? And in this CLT, what did we do? We used to subtract mean of the normal and we used to divide it by the standard deviation, right? And that would give us the standardized distribution, which standardized random variable, which we then said would follow some normal distribution, right? So standard normal, in fact. So now here, I'm not going to use mu and sigma, and I'm going to use alpha n and beta n instead. And thankfully, or maybe unfortunately, we don't have to see how to derive the values of this alpha n and beta n in this subject. So that can be left best to the theorists and people who know a bit of a real analysis and can deep dive into math as well. So now let us try to see what happens. So again, forget about the limiting distribution, forget about the standardization and everything else. Let us look at, this as just a simple problem. So what I'm trying to figure out is a distribution that my xm is less than or equal to x. So my distribution for xm, this would be what? This would be my f of x, right?
Ma'am,
Small x. Yes, Isha?
can you just go back to the previous slide for a second?
All right. You have any questions?
Nothing. I just had to write down the alpha and beta and thing. I wasn't sure whether it was just beta or beta something.
Okay, yeah, all right. So it's n because it actually depends on n. I mean, I'll come to that in some time. So we have this, right? We have probability that my xm will be less than or equal to x. So now what does my xm consist of? Okay, so right now just forget about these and these notations. So whenever I'm talking about xm, just consider as if I'm writing this. So this is my xm, okay? But you guys do know that this xm is basically, the value that I have. So xm is again, just the maximum of these things. Okay. So now if I want to say that my xm, my extreme value of this one particular block that I'm looking at should be less than or equal to this some value x. What does it mean? It means that all of my elements of xm will also be less than the same value small x, right? So I can rewrite this probability as the probability that I observe a x1 less than or equal to x, comma, x2 less than or equal to x, and so on till xn less than or equal to x. And again, remember we are assuming that these events are independent and identical as well. So now first I'm going to use the independence, and this would just become the probability that I observe my x1 less than or equal to x times the probability that I observe my second loss to be less than or equal to x, and so on till the end. Right? And now I'm going to use the identical property and say that each of these x's follow the same distribution f. So I can, instead of writing these as individual, I can just raise them to the power of n. So I have x here, this is 1. Does this make sense? And again, I can just rewrite this as my f of x, right? And I'm raising it to n. So again, remember, this was f of xm, right? We were trying to figure out something about, so this was f xm x, which is just f of x raised to n, right? Where n is the block size. So it is just, the multiplication of the individual CDFs within one particular block. Does this make sense to everyone? But again, now what we have to look at is not the probability that my xm is less than or equal to x, right? We have in a way assumed that we have already standardized it. So what I'm going to write is that my limit n goes to infinity, probability that I observe a value xm minus alpha n upon beta n less than or equal to small x. This is what I'm concerned about. So if you have a closer look, you can actually rewrite this whole thing as, because this and this again are just constants. Okay, remember, these do not depend in any way on this x. So this is just the probability that my xm would be less than or equal to beta n times x plus alpha n. Do you guys agree with what I have written on the board? Which is nothing but f of beta n x plus alpha n, right? So now I can rewrite this whole limiting distribution as limit n goes to infinity, and instead of writing this whole term, I'm gonna write, so remember, this is what I'm writing, the probability that my xm is less than or equal to x, and here I can rewrite this square bracket as this thing. So if I'm trying to figure out the probability of this thing happening, instead of this small x here, I just have beta n x plus alpha n. So what I'm going to have here is f of beta n x plus alpha n raised to n, because we started off with x and what we have is f of x raised to n. So here what we have is this whole thing instead of x. So we are going to have this whole thing with f raised to n. Does this make sense to everyone? Yes or no? So this is actually not the distribution. This is me trying to prove that there exists a distribution. So again, there are some limiting conditions, there are some regularity conditions that these have to satisfy, and then only we know that, some extreme distribution does exist. But again, we know for sure that there is only one distribution which will fit any maximum value that you are trying to model, as was in the case of CLT, right? Any sum of individual values that you want to consider, you would always approximate it to normal, given that the n is big enough, right? So here, what I'm trying to do is that this, given that my n is big enough, this is my distribution. This whole thing realizes the limiting distribution of maxima that I'm considering. And for it to exist, I know that there should exist some alpha n and some beta n, which we don't have to concern ourselves with of how these were, how these were derived, at least for this chapter. So that is the thing. And I think the very captivating thing about this theory is, even though we are talking about extreme events, which looks like as if we're trying to do something complex, have you guys ever seen the CDF of normal distribution? No, right? We have only seen the PDF of normal distribution, and maybe CDF is just written somewhere as integral of that PDF. But we do not have a closed form solution for the CDF of normal distribution. And the surprising thing is that if you try to use extreme value theory, you do see the CDF of these extreme distribution. So this is one advantage that you have. And again, now it's the time to reveal the name of the distribution. It is called generalized extreme value distribution. Not surprising, right? We are analyzing extreme values. So it is usually written as GEV and distribution. So I'll tell you guys why do we have this generalized term here and not something else. So even though, so I guess before we do that, I should take you guys through an example from the book. Yeah, so it's here. Okay. So can you guys read the question? We see that my x follows some exponential distribution with the usual parameter lambda, which is just the rate of occurrence of the events. And again, they have defined what is alpha n and what is beta n. So alpha n here is 1 upon lambda ln n, and here beta n is just 1 upon lambda, okay? And this is true for all of these n. So the question is, we have to figure out the CDF of the limiting distribution of the standardized values of xm. So remember, when they're talking about standardized values, it means this, xm minus alpha n upon beta n. This is just a way to standardize, right? And now we're trying to figure out that I observe these value less than or equal to small x, which again I can summarize as this, we just saw, right? So now again, knowing that, we have exponential distribution in place, let us see what's happening in the answer. So if you have a look here, what do you see? We know that this is true. So I have just written it as it is, copied it from here till here. And now what I'm going to do is, because I've been provided with the values of my alpha n and beta n, I'm going to substitute them here and here, right? So for beta n, I substitute 1 upon lambda, and for alpha n, I substitute 1 upon lambda log of n, right? But again, what do we have now? We have f of this thing. So can someone remind me of what is the f of x of exponential distribution? So if my x follows exponential distribution with the parameter lambda, what is my f of x? It is just 1 minus e raised to minus lambda x, right? So now what I have to look at is f of this whole thing. So what I will get is f of this whole thing. So again, I'm just not going to write that again. So what you will have is 1 minus e raised to minus lambda. And instead of this x, you're going to write this whole bracket. So what you have is 1 upon lambda x plus 1 upon lambda log of n. So you can see that these lambdas would get cancelled and you will be left with what? Minus x plus log of n. And again, because it is e, I know I can rewrite this as this thing. Do you guys agree with this? So this is essentially where you end up here. So 1 minus e raised to minus x minus log n, right? This is what you have. And then I guess,
Ma'am,
yes, Isha?
ma'am, can you just explain why we've taken n tends to infinity?
Oh, why we have taken n tends to infinity. So that is actually, whenever I'm trying to say that, in essence, I'm looking at a limiting distribution. So what happens is so let us go back to CLT. In CLT, if you were looking at, let's say, binomial distribution, what would you do? You have a certain value of n, right? Which if exceeds, then you can approximate those binomial distribution values to normal distribution, right? Which would be continuous. So you were looking at some discrete data, and which is probably something like this, and then you approximate it to this integral, right? In normal, you have integrations. So what happens is these extreme value distributions should have infinite tails. So when I'm talking about tails, I mean this. They should go on till infinite again. And what happens is, traditionally, it's trivial. I mean, it's just a statistical property, I can say, not exactly property, but again, it's just a traditional assumption that the upper bound on these tails is so large that no significant result gets affected if you replace this by infinity. So what happens is basically you want n to be large enough, okay? And you can still put an upper bound instead of tending this n to infinity, but then you would have to do some transformations and, some sort of rescaling to the distributions that we will study. But we don't have that. We're looking at an easier case where we're just assuming that, n goes to infinity, because that in a way makes our life easier, and sometimes that is a good approximation. Sometimes you don't need really complex models, when instead of n going to infinity you would have some upper bound. So sometimes you would still have that, but we don't have that in the syllabus. And I guess, does that answer your question though?
Yes, ma'am, got it.
Any doubts? Anyone else would want to ask? Thank you very much, Isha, for asking that question. What about others? Do you guys feel comfortable with all that we have yet discussed? Any queries? Any thoughts? So now we are just solving for this exponential case. So again, when I said that my x follows exponential distribution, remember this exponential is my parent distribution, the underlying distribution of all the data values that I had initially. And the distribution that now I'm trying to figure out, which is of xm, this is the child distribution that we are trying to figure out, okay? And we'll see what distribution it follows. So what do I have here? I have this thing, right? And what I can do is, so I have 1 minus e raised to minus x, and this I can rewrite as, because I have minus 1 here, it would go in the powers here. I can rewrite this as log of n raised to minus 1. So what I will have is minus x here, and e and log would cancel, and n raised to minus 1 will just go down here. So what do I have? 1 minus e raised to minus x upon n, right? And this is for f of x. But what do we have here? We have f of this thing raised to n. So what will I get? I'll get this thing raised to n. So have you guys copied this? If not, I guess, should I clear it? Or maybe I can just move down a bit here. Okay, yeah. So what do we have now here is, we ended up here, and again, I haven't written limits everywhere, but you will have to write limits everywhere as well. So how do you go from this to this? So remember when we were given a hint in the question. So if you're looking at limit n goes to infinity, 1 plus x n raised to n, you can summarize this as e raised to x. So what is this power? This power is essentially what's there in the numerator over here. So if you draw a comparison, from what we have here. So basically this would look something like, limit n going to infinity, and this would be raised to n, right? So you will have to essentially draw a comparison between this and this guy here. So what will you get? Let me just erase this. Yeah. So what do I have here is limit n goes to infinity 1 plus, instead of this x, what can I write here? So again, remember I have a minus here. So what I can write is minus of e raised to minus x here, right? And all of these things raised to n. Does everyone agree with what I have written? Taking that as a yes. So now if you were to summarize this, what would you get? So whatever you have here comes in the power of e. So here you would write e raised to this term, which is just minus of e raised to minus x. So this is what is the CDF of the standardized values of xm. And this distribution is actually, known as a Gumbel type GEB distribution, and we'll have a look at that in detail again. So it is defined as Gumbel because our parent distribution is exponential, and whenever you have an exponentially decaying tail, that corresponds to a Gumbel type maximum value distribution. So again, remember when I stated, the actual distribution that we were studying, I said that it is a generalized extreme value distribution. So why do we say generalized? Because this one distribution encompasses 3 other distributions. So this is, again, remember the very first method that we're studying, the block maximum method. And now we are going to have a look at this GEV distributions CDF. So I define my function as h of x, and I'll just write this. I don't remember this. I'm just gonna write it from the book. So what do I have? I have it as e raised to minus of 1 plus gamma x minus alpha on beta and this is observed when gamma is not equal to 0. So I'll tell you guys what it means if you have gamma equal to 0 and what it means if you have gamma not equal to 0. So you see, when you have gamma not equal to 0, you have 3 parameters, right? Gamma, beta, and alpha. So the parameters that we have are alpha, beta, and gamma. So these are 3 different parameters pertaining to the location, scale, and the shape of the distribution. So again, trying to create an analogy between the CLT, over there, your mean was the location parameter, it would determine where your distribution would be. So if my mean is here, my peak would be here. But if let's say my mean was here, then my distribution's location would be a bit to its left. So this is my location parameter. And similarly, this is my shape parameter. Sorry, this is my scale parameter, which will measure the width, basically, the variance. And this gamma right here is my shape parameter. So this is the most important parameter. And it is kind of similar to skewness, right? So if you see, I have written gamma equal to 0 here. Does anyone remember what is the value of skewness for my normal distribution? Anyone? I guess it shouldn't even take you this long to figure out the
0.
value. 0, exactly. Thank you very much. So it is 0, right? So again, you're going to observe that, if your parent distribution is normal distribution, you will meet this condition because your gamma is 0. But again, that's not the case always. you would still see this even if your parent distribution is not normal, but something else. But again, there are some restrictions to what that something else can be. It cannot be Pareto, or it cannot be, uniform distribution. So we'll have a look at that again in some time. So remember, just count the privilege that we have here, okay? In this CLT, we assumed, that my limiting distribution is normal, and we didn't know its CDF as well. Over here, we have an explicit formula for the CDF of my extreme value distribution. And it is almost magical that given any X, given any parent distribution, the child distribution will always be a generalized extreme value distribution. And it can be nothing else if you are trying to, figure out the distribution of the maximums. This is the distribution that you will have for sure. There's nothing else that it can be. So this is a very, very powerful theorem, I would say, and this is what is dictated by the extreme value theorem, which was actually, so it goes back to a guy called Tippett, who wasn't actually, a statistician. Maybe I don't recall if he was a statistician, but what happened was he was placed in an industry, a yarn industry. So when I'm talking about yarn, it means YARN. And what he had to do was he had to see the yarn's breakability and its strength, basically. So if you try to twist that yarn again and again, he had to see at what point that yarn bundle breaks into two. And that would happen only if the last thread, which forms the part of the yarn, breaks, which is kind of an extreme event, right? So that is what he was assigned to, work with. And he happens to had done his MSc in statistics under Fisher and Carl Pearson. So Carl Pearson is the guy who actually devised, the Pearson coefficient that you guys must have studied in CS1. So that is where he and Fisher then, got together and they devised this extreme value distribution. So it also has another name which goes by Fisher-Tippett distribution. So this is just, useful for the cases where so again, now the fact we know is that if my parent distribution is any distribution, I know for a fact that the distribution for my extremes is going to be extreme value distribution, my generalized extreme value distribution, right? So what happens is sometimes, even if you do not know your parent distribution, you can easily assume that the distribution of your extremes is going to be generalized extreme value distribution. So this is again, I would say sort of magic. So if you try to work with the data and everything, I guess you guys will study in R as well. The same thing. I think you guys will just have to use the built-in packages. EVT, you have some packages, and yeah, you can just much easier as well in R, I would say, than it is going to be in the theory class where we're going to sit and derive, let's say the PDF. Now we will see the PDF of this distribution, but I guess let's leave that for tomorrow. Maybe we can study the graphs today. Okay, so now if I'm saying that my gamma is either not equal to 0 or it is equal to 0. So if it is not equal to 0, it can either be greater than 0 or it can be less than 0, right? So now we'll have a look at what happens if this is the case. Okay, let me just draw some graphs and I'll have to draw those accurately. So just give me a minute. So remember what I said? I said that this generalized extreme value distribution encompasses 3 distributions. And now we know that those 3 distributions will be one where gamma is equal to 0, one where gamma is less than 0, and the last one where gamma takes a value which is greater than 0. And we'll see the usefulness of these 3 different cases by the properties that its graphs follow. because at the end, we want to know about the data set that we have, and it should ideally fit this thing. So what you will have, so what you will be doing in the practical sense is, you won't know which one of these three distributions is your actual child distribution. But you would know for sure that it will be generalized extreme value distribution. So you can just fit this distribution and use the maximum likelihood method to figure out the values of gamma, alpha, and beta. And then based on the value of gamma, you would know what distribution it is, right? And let us see what are those three different distributions that you see, that you can actually encounter. So let me first draw the actual distribution, which would be, observed if my gamma is equal to 0. So it would be something like this. So again, it looks like it is a symmetric, but it is a bit skewed to the right. It is not exactly symmetric distribution, but it has a gamma value of 0, and such kind of distribution is actually, Gumbel type GEV distribution. So this is Gumbel. And now let me draw the another one where you have your gamma value greater than 0, and these are known as Fresher. And this would have tail starting from here, but a higher tail over here. So you see, the tail behavior for this Fresher type distribution is a bit heavier than what it is for the Gumbel case, right? And now if you have a look at gamma less than 0, gamma less than 0 case, which will be viable, it would look something like this. So it would have a heavier tail starting from here. And yeah, it would cut off right. So now we are trying to analyze the behavior of decay of these graphs. What do you observe? You see that your pink graph decays slowly. So what you will be actually saying is, instead of using the word slowly or faster or this, you would say that it decays exponentially. And in Fresher, you see it doesn't decay as faster as in the pink case, right? So what's happening here is, when you're here, it is already so low. But if you're here, this is still yet to, reach its level to the x-axis. So if you are Fresher, you have a tail which is declining, with power. So if let's say you have a Pareto type parent distribution, you'll be using Fresher because it has in its power x. So it's called a power-tailed distribution. And here if you observe with gamma less than 0, it decreases right after reaching its peak, right? Instantaneously it drops off. And here again, I think I doesn't look clear, but here also there is a value particular, beyond which it's 0 always. So for this guy, beyond this, the PDF is 0. And we'll have a look at, why is this the case once we figure out the PDF of these guys. So we'll figure out the PDF for this case and this case separately. And then we'll have a look at what is the value of this in this cutoff that we have to look at in respect of the three distributions which encompass the generalized extreme value distribution that we're trying to have a look at. Does this make some sense? I mean, we haven't yet studied it fully, but I just want you guys to, have some sort of idea of how these things look like. So let me maybe fetch something from the book. So if you have a look, I guess they have, yeah, we have this. Yeah, so remember when I drew, a Fresher type, oops. Yeah. So you see there's a cutoff here, but again, that cutoff need not be fixed always. So it again depends on the parameter values that you have. It will depend on alpha and the beta values that you encounter. And you see it decays slowly, right? So this is sometimes used to model, extreme financial loss, because you saw that this has heavier tail, right? And in finance, whenever we're looking at asset returns, they tend to have fatter tails. They tend to be leptocotic. So this is the fresher type of GEB distribution that you're going to use. So they have, I guess, written, so if you see gamma is 0.5, which is greater than 0. And now if you have a look at the next distribution that they have shown, which is Weibel type GEB. So you have gamma value less than 0 as expected and a cutoff right here. So again, the way it decreases and it goes down instantaneously or whether it's a bit slower depends again on the parameter values alpha and beta. And this, if you see, we have an upper bound, right? So what kind of losses do you think can best be described using Weibel type GEB? The kind of losses where you might have reinsurance treaty in place, right? Because you know that your losses would not exceed 100 or your losses would not exceed 150 for sure. Because I know that if my loss exceeds 100 or 150, the rest of the amount might be insured, against the reinsurance company. So you won't have to bother with that. So your distribution will just, be limited till 100 or 150 or whatever your limit for the or whatever your retention limit is, right? So that is one another distribution. And the last is this Gumbel. Yeah, so here you can see, right? It's not exactly symmetric, but the skewness is, 0. Not exactly, but yeah, you can actually say that, the skewness is 0. So it's gamma is 0, which is a measure of skewness. So it is almost 0. And over here, you will again have different sets of values for alphas and betas. But again, this is kind of used for the products that will quickly, wear out after a certain time period or after a certain age. And this Gumbel type GEV is the one which is usually used to model earthquakes or the other natural disasters as well. And again, I would say, this goes on, I mean, it's just magic, how any distribution you give, any value for the excess, the maximum limiting distribution will always be a generalized extreme value distribution. And again, remember, here, there is no bound. So there is no bound in the tails. For Weibel, you had an upper bound, and here you had a lower bound. So we'll try to figure out these bounds values as well. And I guess, let me see how much time we have. It's already 8:25. I guess we can still derive the PDF of these h of x today. Would you guys mind if I take 5 minutes more? So let us try to derive, the PDF here. And I guess it's not going to take much time. I mean, it's really, we have E. So to differentiate e raised to x is just, e raised to x. So let us see what happens. So again, I'll have to look at two cases, right? So my h of x is some value for my gamma not equal to 0 and for my gamma equal to 0. And now I'm trying to figure out my h of x. So let's say this is my first case where gamma is not equal to 0. And here maybe I can just analyze it down here where my gamma is equal to 0. Would you guys want to actually try this out on your own at home? Or do you guys want me to dictate it now itself? So, okay, maybe what I can do is just write what we have to differentiate first. So here we are trying to differentiate d by dx of e raised to minus of 1 plus gamma x minus alpha upon beta raised to minus 1 upon gamma. Okay, and here my h of x will be just d by dx of e raised to minus x minus alpha upon beta. Okay, so this is, I guess, not that difficult. So maybe we can do this thing first because this seems easier. So remember, what is my d by dx of e raised to 2x? I'll write this thing as it is, which is e raised to 2x, and then I'll do d of 2x by dx, which will give me 2 times e raised to 2x, right? So the same chain rule I'm going to apply now here. And what do I get is, first I will just rewrite this thing as it is, right? Which is e raised to minus of x minus alpha upon beta, right? And then what I will do is, I will differentiate this numerator here, this power, sorry. So I have d of minus of e raised to minus x minus alpha upon beta by dx here. And what will I have again? So this thing will be, as I'm just erasing that. I do not want to write that whole monster again. So I have this thing, and now I will just have to differentiate this. So I'm keeping this minus sign here intact. And now I have to differentiate this. So if I have to differentiate e raised to something again, I'm just going to write that thing as it is, right? X minus alpha upon beta. And then again, I will differentiate the numerator using chain rules. This minus will turn this minus into plus, and I'll have to differentiate this thing. So x upon beta will just give me 1 upon beta. So I have 1 upon beta here. So what do I get at the end is something like 1 upon beta e raised to. So now what do you have? This is not actually plus, okay? You're just multiplying this term and that term together. So you have e raised to this thing and you have e raised to this thing. So e raised to x plus e raised to y is just e raised to x plus y. So you can write this as minus of x minus alpha upon beta plus e raised to minus of x minus alpha upon beta. Does this make sense to everyone? So maybe what I can do is, I guess, first of all, here I should write a minus. Maybe we can highlight certain terms, right? So this term from here is precisely what you have here. Okay. And this term from here is precisely what you have here. Okay. And this 1 upon beta is what you have here. Does this make sense to everyone?
Ma'am, can you go back once to the previous page?
Sure. Yeah.
Yeah, got it. Thank you.
Anyone else? Any doubts? I mean, it's really easy, but the only thing you have to take into consideration is because it is e raised to e, you have to use chain rule multiple times. So what we did was, this is just this thing as it is. Okay. Then you differentiated this guy, and this is its differentiation. So you had minus here, and you wrote this thing as it is, which is this here, and you differentiated this power. So you got this minus again, which made the previous minus into plus. And then because alpha and beta are just constants, you only had to differentiate x and beta, x upon beta. So if you differentiate x upon beta with respect to x, what you get is just 1 upon beta, right? And that's it. You're done with the differentiation. Now you just have to collate terms. So 1 upon beta comes here, and this is e raised to x plus e raised to yellow. And what you get is e raised to blue plus yellow. Does this make sense to everyone? I guess if this is a bit of a hurry for you guys, I would say that, just try to solve this differentiation by your own at home after this class is finished. And then if you do have any doubts, just put it in the WhatsApp group or just message me. And Really easy, not something to worry about. Does this make sense to everyone? Yes or no?
Yes, ma'am.
Thank you very much.
Yes,
So
ma'am.
do you want to try to do this, or would you all want to try this at your home? Maybe let us just do it in the classroom now itself. And it's fine if you want to leave the class now. Not how much of it's gonna it will be get recorded anyways. So now if I have to differentiate this guy here, first of all, because I know it is e raised to something, I will write this whole thing as it is. So what I have is e raised to minus of 1 plus gamma times x minus alpha upon beta raised to minus 1 upon gamma. Okay. And now what I will have to do is I'll have to differentiate this whole numerator term. So what I get is minus here. And now this is something raised to something, right? So if I have a differentiation of x raised to something, I'll use chain rule. So let's say if I have to differentiate x square, what do I get? I get 2x. This thing comes in front and you have a minus 1 here. So this will be 2 minus 1, which is just 1 here, right? So the similar thing I'm going to use now with this numerator right here. So what do I get? I'm putting this minus here, and this is my power term, which will again come here, and I'll write this thing as it is, which is 1 plus gamma times x minus alpha upon beta. Okay, and this bracket will be raised to minus 1 upon gamma minus 1, right? Do you think this is the end of the differentiation, or have I missed something?
X coefficients.
X coefficients, right? Because using the chain rule, I not only have to differentiate, I have to differentiate this whole power term, right? And what I differentiated now was the power term. And now I'll have to, using the chain rule, differentiate what's in the bracket as well. So differentiation of 1 is 0, and differentiation of gamma x upon beta is just going to be gamma upon beta, right? So now let us see what terms cancel. This minus and that minus would cancel, right? This gamma and that gamma would cancel. That's it. Nothing else cancels. So this is what you will be left with. And that is your final answer, I would say. So you have e raised to minus of 1 plus gamma x minus alpha upon beta raised to minus 1 upon gamma. And here everything got cancelled. So what you have is 1 plus gamma x minus alpha upon beta raised to this thing, which is minus 1 upon gamma minus 1, and you have upon beta. So what you can maybe just do it here instead, write 1 upon beta. Does this make sense?
Yes.
Yeah, so I guess that's all for today. And yeah, and we'll have